In this video, I'll cover forward probabilities, a useful way for computing the observation likelihood of a sequence. I'll discuss the intuition as well as the formal algorithm for computing them, and then work through a case example. The observation likelihood for a sequence is just another way of saying what's the probability that this particular sequence of observations was generated by the model. Answering this question is particularly useful for two tasks: sequence classification and selecting the most likely sequence. Sequence classification allows you to use HMMs to determine which category a sequence of text belongs to. To do so, you can create an HMM for each class. For example, if you're doing sentiment analysis, you might build one for positive text and another for negative text. Then you figure out which HMM is most likely to have generated your test sequence of text, and the one that is most likely ends up being the class label that you assign to the instance. Automated speech recognition is one common scenario in which HMMs are used for sequence classification. Selecting the most likely sequence is in some ways the reverse of this. So rather than considering multiple HMMs, you consider a single HMM and multiple test sequences. The task then is to decide which of the test sequences is more likely to have been generated by the HMM. This is also useful for speech recognition, and you can imagine it being similarly useful for any sort of text problem where you want to find a sample that's the best fit for a given class. So the question then is, how can we compute the observation likelihood? So one naive solution would be to just consider all possible state sequences that a model could have conceivably traversed in order to generate the given observation sequence. For each one, you could compute the probability of the state sequence multiplied by the probability of generating your observation sequence using that state sequence. Then you could sum over all those probabilities to get your observation likelihood. It's in theory a fine solution, but it's very computationally complex. So a more efficient solution is to use something called the forward algorithm. The forward algorithm is a dynamic programming algorithm, just like minimum edit distance was. It in principle does the same thing as the naive approach I just mentioned, but it relies on the Markov assumption to do so with far fewer compute operations by assuming that the probability of being in a state at a given time relies only on the probability of being in each possible state at the previous time step. To see how that works, we can work through a fun example from the course textbook. So here's the premise. It's the year 2799, so I guess we're still here at that point. And you're a climatologist studying the history of global warming. You need to figure out what the weather in Baltimore was like during the summer of 2007, but you don't have any records for it. You do, however, have some hypotheses about how likely it was in general to move from a hot day to a cold day, and so forth during that era. You have a few HMMs that you're considering as you fine-tune your model for that. Then, all of a sudden, you have a major breakthrough. You find the diary of Jason Eisner, who happens to be an NLP professor at a university in Baltimore. And in his diary is just a list of how many ice cream cones he ate every day that summer. So you decide to use the observations from a particular 3-day sequence to see how likely that sequence was to result from your leading HMM. Here's our 3-day sequence of observations. On day 1, he ate 3 ice cream cones. On day 2, he ate 1 ice cream cone. And on day 3, he ate 3 ice cream cones again. So here's our current HMM that we're working with our hypotheses about weather patterns represented as the transition probabilities, and our hypotheses about how likely Jason was to eat 1 ice cream given that it was hot and so forth, represented as observation likelihoods. What we need to do in order to figure out how likely it is that our sequence of observations from the diary matches our current leading HMM is to compute forward probabilities. So let's go ahead and formalize our algorithm a bit. Let's let alpha sub I of j be the probability of being in a given state j after seeing the first t observations, given our HMM, which we'll represent as lambda. The way that we compute our alpha function for j is by summing over the probabilities of every path that could lead us to it. We can break this down further by saying we have a set of states from 1 to n, and we're going to loop through them to keep a running total. For each state I and n, we'll do 3 things. We'll get the previous forward path probability for this state from the previous time step. We'll get the transition probability from state I to our current state j, and we'll get the observation likelihood for the observation at the current time step being observed for the current state j. We'll multiply these 3 things together, add them to our running total, and just repeat for all states from 1 to n. So in slightly more concrete terms, we can look at this in algorithmic format. So here we have the pseudocode for the forward algorithm. We see that we start by just creating a probability matrix of size n plus 2 by t. So we need the total number of states plus 2 as one dimension, and the total number of time steps as the other dimension. Next, we'll initialize everything for the first time step. So we'll loop through all of our states, and for each state, we'll initialize the forward probability to the product of the transition probability from the start state to the current state q times the observation likelihood that the first observation in our sequence was generated by state q. Then we can move onward to the rest of our sequence. For each time step from time 2 all the way to t, our last time step, we'll loop through each state q. Within that loop, we'll set the forward probability for the given state and time step to the product of the forward probability for state q prime at the previous time step times the transition probability from q prime to q times the observation likelihood that the observation at the current time step was generated by state q, summed across all q prime from 1 to n. Finally, once we're finished with that loop, we'll set our final forward probability to the sum of the forward probabilities we computed for all states q from 1 to n at time step t. We can work through an example of that now to see what the process looks like in even more concrete terms. So now we have this forward trellis that you see here. We have a bunch of states at different time steps, and we have a sequence of observations with one observation per time step. For a given time step t, if we were computing the forward probability for state j, the relevant information would come from the states at t minus 1, the current state itself, and the current observation itself. So we'll set things up according to our ice cream problem. So for convenience, I stuck the HMM over in the top right corner. We have 2 main states here, hot represented as H and cold represented as C, but we also have a start state, and then we'll add an ending point as well for our final forward probability output. We can't ever transition to or from the states with the dashed lines at the specified time steps. For example, at time 2, we can't end things right then and there because we have 3 observations in our sequence. So we'll start out, and the first thing we need to do is compute the forward probabilities for both H and C at time 1, where we observe that Jason ate 3 ice cream cones. To do that, following the algorithm we saw a couple slides ago, we'll multiply the transition probability from start to H, which is 0.8 according to our HMM, times the observation likelihood of eating 3 ice cream cones given that it's hot, which is 0.4 according to our HMM. That'll give us the forward probability for H. To get the forward probability for C, we'll multiply the transition probability from start to C, which is 0.2 according to our HMM, times the observation likelihood of eating 3 ice cream cones given that it's cold, which is 0.1. So this means we computed the following forward probabilities at time step 1. So now we can move on to time step 2, where Jason ate 1 ice cream cone. And just like previously, we'll multiply the relevant transition probabilities and observation likelihoods. So transitioning from H, we'll multiply the transition probability for remaining in H times the observation likelihood of eating 1 ice cream cone given that it's hot, and then we'll multiply the transition probability from H to C times the observation likelihood of eating 1 ice cream cone given that it's cold. Coming out of C, we'll multiply the transition probability from C to H by the observation likelihood of eating 1 ice cream cone given that it's hot, and then we'll multiply the transition probability from C right back to C by the observation likelihood of eating 1 ice cream cone given that it's cold. To get the forward probability for H at time step 2, we'll multiply the forward probability for H at time step 1 times the product we already computed for remaining in H, and then we'll multiply the forward probability for C at time step 1 times the product we already computed for moving from C to H, and then we'll sum those two values together. Likewise, to get the forward probability for C at time step 2, we'll multiply the forward probability for H at time step 1 times the product we already computed for moving from H to C, and then we'll multiply the forward probability for C at time step 1 times the product we already computed for remaining in C, and then we'll sum those values together. We'll repeat this process once again at time step 3, our last time step, where Jason once again ate 3 ice cream cones. And ultimately, we'll find the values that you see here. So now we just need to compute the final forward probability, representing the observation likelihood of the sequence of 3, 1, 3 occurring given the HMM we've been using here, to see how likely it is that this sequence was generated by the current HMM. All we need to do for that is just sum up the forward probabilities for the individual states at the final time step. And we find that the result isn't actually a super high value, so maybe we still need to do a little bit of work to figure out the best HMM to model this situation. So as you can see from this video, computing forward probabilities is a nice, straightforward dynamic programming approach to figure out how well an observation sequence fits a given HMM.